Hi, welcome to my channel. This is Moses, and I will be teaching you engineering mechanics in this series. This is the first lesson, and I will give you an overview, sort of an introduction about what this engineering mechanics is all about. Engineering mechanics is essentially divided up into two parts, which is statics and dynamics, which in turn, dynamics is divided into kinematics and kinetics. So what does this really mean? To understand this division, I think we should go back to the basic quantities in physics. I'm sure as a student of engineering or someone who is aspiring to learn engineering, you must be aware of these physical quantities such as displacement, velocity, acceleration, force, mass, momentum or impulse, and work or energy. Now all these are physical quantities. We'll look at statics, kinematics, and kinetics, the last two being a part of dynamics, right? So how do they all relate to these physical quantities? Statics primarily deals with forces. Okay, that's the primary purpose of statics. Whereas one might think that we also consider displacement and velocity as well in statics. But that is not quite true, because you can have, for example, in an aircraft, if you are analyzing the chair of the person who is sitting, the seat in the aircraft, the whole aircraft is moving along with the chair, obviously. So there is an absolute displacement of velocity there, but there is no relative displacement and there's no relative velocity. So in order for you to say this is statics, there must be no relative displacement and no relative velocity. In which case you can just analyze the forces, and that is what is statics all about. Whereas in case of kinematics, kinematics is essentially about motion. Motion in terms of displacement, velocity, and acceleration. We do not look into the forces which are causing it, but only acceleration, of course, which is responsible for the motion in terms of its displacement and velocity. They could be linear velocity, linear acceleration, also rotational velocity, rotational acceleration as well, but that is all kinematics. Then if we consider the rest of the things like force and mass and momentum, impulse and work and energy and all the rest of it, then it is kinetics. So kinematics and kinetics put together obviously is dynamics, and dynamics and statics together is mechanics. So this is one way to understand mechanics in terms of these divisions. Okay, right. So let me introduce you to another way of looking at various types of mechanics. Now, if you consider the first row of these blocks, three blocks on the top row, we will consider particles, as in point masses. A point, they're just points, right? They don't have dimension. They don't have length, breadth, and depth. It's only a point. Whereas in the bottom row, then, we will consider bodies, as in they have finite length or depth or width, etc. They are finite-sized bodies. Now, in the columns, the first column is about rigid bodies. Okay, rigid as in there is no deformation when the forces are applied. At least we will ignore or neglect the deformation caused, deformation as in it doesn't deform. That's what I mean. So the deformation of the body is ignored or zero. Whereas if you want to consider the deformation of the body, then you call it flexible body. It doesn't mean that it deforms too much. Whether it deforms too much or too little, it doesn't matter. But that's a second column here. And the third one obviously is if the body is fluid, then we are entirely in a different domain. Now, all of this is mechanics. However, we need to remember that there are no flexible particles or no fluid. We don't analyze the fluids just as particles without considering the body. Therefore, we have blackened out those two. And so what we have then is the rest of the things, statics and dynamics of particles, rigid body mechanics or multi-body mechanics, solid mechanics. If it is flexible, if there is deformation involved, then we'll call solid mechanics, or sometimes they call it mechanics of materials, although there is a slight difference between solid mechanics and mechanics of materials. But essentially it is about studying bodies which can be deformed by applying force. And finally, of course, the last one is fluid mechanics. All of these are mechanics. Now, let's consider rigid body mechanics, whether it is particle or whether it is it's a finite sized body. Let's consider those two red ones and split it up a little bit further, right? So I've got 6 more blocks here to consider. So I've got the first row, so first column as particle, second column as a single body now. So instead of calling it a body as in the previous case, we are saying single body as opposed to a multi-body, where multi-body means there are multiple bodies interacting with each other. So the middle one is about only single body. There are no other bodies interacting with it. Okay, so if you take these 3 classifications on the columns, and then so they are all rigid bodies, by the way. So there is no flexible as in deformable body, neither is there any fluid here. We're only talking about rigid bodies now, which is in the scope of our engineering mechanics. If you look at the rows, the bottom row, let's say it is about fixed bodies, as in both particles and the single bodies, multi-body, all of them are fixed. Whereas the top row is you have these bodies moving. If this is the classification, then we have all these names, and I will explain one by one what these are. So in the first case then, we have fixed particles, essentially statics of particles, where our focus is on equilibrium of forces. So it looks like this. We want to see whether this bracket which is attached to the ground is going to move or stay stationary. So all these forces are acting in different directions. We want to ensure that that point, red point there, isn't going to move. Or we want to see, we want to design this in such a way that that doesn't come off. Okay, that's the purpose of this analysis. There is a point. So we don't have to analyze everything, but we just need to understand whether or not that point will move or not. Is it static? Is it in static equilibrium? Is the question that we will look at. Now, if it is a particle, but it is dynamic, as in if it is moving, then we have a problem something like this, where you have this green bracket that is actually, it moves only in that semicircular path, and it is attached to the spring as well. And the mass which is hanging below tries to bring this sleeve to the center, whereas the spring doesn't allow it, because if you try to move it, the spring will either get compressed or stretched. And therefore, there will be a position of the point A where the whole thing comes to an equilibrium. That is, we must find the point A, the position of the point A at which the whole system will be in equilibrium. That's the sort of a problem we're looking at. Or perhaps if you want to actually move the sleeve up to the top and leave it, then how does this point A move up and down in a dynamic fashion? It could be like a vibratory, it's a sort of a vibration. It's a cyclic oscillatory motion sort of a thing is what we will experience. And so that is also the subject of particle dynamics. That's what we're looking at, dynamics of particles. Now, if it is a single body and if it is fixed, you have something like this. Okay, it's a single body now. It's a 3-dimensional body, has a length and width and all that stuff. It's no longer a particle, but we have multiple forces acting upon it at multiple locations in different directions, and we want to know whether or not this body is in static equilibrium, as in whether or not all the forces acting on that body are balanced, and if it is balanced, obviously it will be static. Okay, and if we look at the single body dynamics where there is motion involved, you have something like this. This is a crankshaft, or you could take a flywheel as an example, where this is rotating and there are a lot of dynamics involved. because of the mass that is not at the center. As you can see, if you draw the longitudinal axis line, a lot of mass is away from that line, because of which the crankshaft will experience wobble. And in fact, that wobble is that is purposely designed in order to balance the automobile engine. Okay, so the point is, when you analyze something like this, you're talking about dynamics of a solid body. Dynamics is a rigid body dynamics. Okay, now coming to the multi-body then. Multi-body, if it is fixed, it is static. What is an example of a multi-body static? So this is the one. It's a truss, where there's a train station in Europe, and you have all the beautiful structure here built, and the multi-bodies are basically different members of the structure, the columns and the different elements within the truss framework. And those are different multi-bodies, and they're all connected to each other, either welded or hinged or whatever that might be. And we want to analyze whether this structure will bear the load, and bear the load as in whether it will be stationary and it won't collapse with the loads applied. That's the interest that we have in analyzing this sort of a problem. Also, this is another example of a structure, multi-body static structure. And finally then, multi-body moving system, where multiple different bodies are attached to one another or interacting with one another, and they're all moving, or some of them are moving with respect to one another, right? So for example, the landing gear of an aircraft, when it lands, obviously you will see these two wheels are tilted like this. It will move up and down. Also, this the whole assembly can be retracted back inside the aircraft, and it can be pushed back as well. And so there are a lot of links that are connected, and there's a mechanism involved. And so we have these multi-bodies, multiple bodies which are connected with each other, and therefore we're looking at it as a mechanism. And finally, we have this robot, is our Boston Dynamics robot. So if you go back actually to look at various subjects here, we have dynamics of particles and equilibrium of forces in the particle case, fixed and moving. If it is a single body, we will do the same equilibrium of forces, static single body scenario. If it is a dynamic thing, then we have rigid body dynamics as a subject. And if it is a multi-body fixed, then what we have is a mechanics of structures, or mechanics of trusses and mechanics of structures as a subject. And finally, if it is moving, we have the subject of mechanics of machines, or theory of machines, as some people would call it. So all of these are part of mechanics. Okay, we have created this framework in order to understand which subject falls where under what conditions. Thank you for watching, and I will talk to you in the next video.